Well, hello everybody. What I'd like to do with you today is I'd like to cover section 9-6 over log applications. Really what we're going to be doing today is we're going to be given some information and we're going to assume that this represents a continuous growth model. And since we said continuous, this will be the formula that we'll be using over and over and over today. A in this case is going to represent some value at some future time, and our P is going to represent our value at the current time. And of course, interest rate is our growth factor or our decay factor, and of course T is going to represent the time. I've only got 4 of these, and then we decided not to give you an assignment over them because there are some on the review packet. So after this video, I'm hoping it's 20-25 minutes or so, we'll have you work on your review sheet, and we are already ready for our logarithm test next class already. So time's really flying. So hang with me as we go through this, and we'll see what you think. Look at your first example there. It says the population of the United States reached 250 million in 1990. It was growing at about 1% per year. The Census Bureau estimated that the 300th million American was born at approximately 7:46 a.m. Eastern Time on October 18th, 2006. What was the actual growth rate during that period? Estimate the population for this year also. So kind of 2 questions here. One, we'd like to find the growth rate between those years. And then 2, we would like to estimate this year's population. Here's how I'd like to attack these kind of problems. We have ideal on there. We're not going to write out all those steps for that. I'll have you write out some information though. I know that we're going to use this formula, our continuous change model, PERT. If you will, off to the side, list the items that you know. I know that it's continuous growth, so there's my formula. Read back through there and see if you can decide what we're trying to find and what we're given. The first question there was, what was the actual growth rate from 1990 to 2006? So we would like to find the R value, which represents our growth rate. Let's list the other things that we know. It looks like we started out at 250 million based on this information, so I know my p-value is going to be 250 million. Our future amount value happens to be 300 million. I know R stands for my interest rate, and it looks like in this case T is going to be from 1990 to 2006. So T is going to be 16 years. So what I'd like for you to do on these is list the items that you know off to the left or across the top. Now, if you will, come in and plug them in. I know A is 300 million. I know that P is 250 million. We got E for our continuous growth. We don't know our R value, but I know my T value is 16. We are now going to solve this. So to solve this, I'm going to divide both sides by 250. You'll find that you can skip over some numbers. 300 million, 250 million. Well, once we divide, 6 of those zeros are going to cancel off anyway. So right now I'm at 1.2 equal e to the, I'm going to write this a little cleaner, 16r. We would like to find this growth rate exactly and as a decimal. So I'm going to take the natural log of both sides to get rid of that e. So I got natural log of 1.2 is equal to 16. Well, it looks like my growth rate is 1.2, natural log of 1.2 over 16. The natural log of 1.2 over 16. We're going to use that exact value in our formula. In terms of your calculator, guys, easy to type that in. Natural log of 1.2. Make sure you close that parenthesis off, though, and then go ahead and divide that by 16. So it looks like my growth rate is approximately 1.1395%. So there's my growth rate. Here in a second, I'll ask you to write a sentence saying that. We'll say that the annual growth rate was approximately 1.1395%. Well, let me come over here now. Here's our model then. Our model is going to be the amount at any time I'd like to talk about is 250 million e to the, keep the r value in there, natural log of 1.2 over 16. That is a ugly 1.2. That's one bad thing about this inner right board. Times the amount of time that you're looking at. All of this is an exponent. Remember that. All of that's an exponent. Now they would like for us to estimate the population this year. So here's what we need to type into our calculator. I need to type in 250 million e, and then your calculator should put a parenthesis there for you. Natural log of 1.2 divided by 16 times the number of years from, so 26. So look at that real fast. Now here's how it should look in your calculator. I'm going to take 250. Second, let me get to my e to the x, wherever that is. And I'm just going to type in what I have there. Natural log of 1.2, close that off, divided by 16 times 26, close that off. When I hit that, it looks like the estimated population, approximately 336.2 million people. Remember this number here in a second, because as soon as I touch my screen, it's going to hide my calculator. But so it looks like my population in the year, let me put that A since that's what we used, looks like the amount of people in 2016 is going to be approximately, what was that number? 336.2 million. Now what I'll ask you to do, guys, is put our answers in the form of a sentence. So it'll look something like this, kind of like we did way back at the first of the year. The annual growth rate was approximately 1.1395%. So there's the answer to the first part of the question. The second part of the question, the estimated population of the United States in 2016 is approximately 336.2 million people. So that's going to be our job today. It'll be a continuous growth model. Figure out your A, your P, your T, find your R value, and then we've got our model. Skip on over to number 2. Number 2 is a little easier than number 1. It says, what rate to the nearest tenth would yield at least, keep in mind that number right there, guys, at least $5,800 if $4,000 is invested for 8 years. We're assuming continuous growth today. So come off to the side. I know I'm using this formula again, continuous growth model. Let's list everything that we know. I know that my future amount is $5,800. I know my principal, my amount right now is $4,000. We're looking for our interest rate again. And I know that we're dealing with 8 years. So scribble down those numbers if you would. Now let's go plug them in. So let's go 5,800 equal 4,000 e to the r times 8. I'm going to divide both sides by 4,000. And then you really know the next step. I'm going to take the natural log of it and divide it by 8. So I'm going to be at 1.45 equal e to the 8r. I'm going to take the natural log of each side. So I'm at the natural log of 1.45 equal 8r. So r is going to be the natural log of 1.45 divided by 8. Now, If we type this in our calculator real fast, let's go the natural log of 1.45, close that off, divided by 8. Remember, it wanted to the nearest tenth. Normally, we would round this to 4.6 because the number after the 6 is in a 5 or greater. But if you use 4.6, you're not going to get 5,800. You're going to get a little bit less. So the interest rate that I need to round that up to the nearest tenth. So I'm going to need approximately 4.7%. If I rounded to 4.6, I won't get to 5,800. I'd be just a little bit shy. So to answer this question, on the next slide, I cheated and typed them since it's a video. The interest rate needed to grow to $5,800 is at least 4.7%. So just be careful on answering the questions, but that's going to be how we'll go. I'll show you the long way, short way on number 3 and number 4, but they're going to be the same type of problem. So here goes. It says a sample of radioactive material has a half-life of about 1,400 years, meaning every 1,400 years our sample is going to decay to half of its value. An initial sample weighs about 6 grams. Find a model for the decay function for this material, then find the amount left after 4,200 years. Then it also says how long will it take to decay to 1.5 grams. So if you really look at it in here, guys, there's kind of 3 problems in here. 1, they want us to find a model. 2, then they want us to figure out how much is left after 4,200 years. And then last but not least, they would like for us to, how long will it take to decay to 1.5? This one, since all the numbers are half of the previous number, you could really do this one in your head. We're going to go through the model, so I can mention a shortcut though. So come off to the side and let's list the things that you know. I know that my future amount is 3 because my present amount was 6. Once again, we're looking for our interest rate. And our time is 1,400 years. Once again, it's a continuous growth model. So let's plug those numbers in. Looks like my A value is going to be 3. My P value is going to be 6. E to the, we don't know our R, but our T value is 1,400. I'm going to speed the process up. You know I'm going to divide both sides by 6 and get 0.5. And then you know I'm going to take the natural log of each side. Look at what happens on this, guys. Let's not use a capital R. I'm going to take the natural log of both sides, so I'm at natural log of 0.5. Equal 1,400R. So I'm going to divide this by 1,400. So there's my R value. Once again, we're going to keep this exact. We can run it through our calculator to get an estimate of it. But I kind of want to show you a shortcut right here. Now, the shortcut only works on half-lives. Check this out. It says it had a half-life of about 1,400 years. Well, look at what we come up with after all this work. I had the natural log of 0.5 over 1,400 years. Whenever you're dealing with half-life, it'll always be the natural log of 0.5 over whatever your half-life is. We'll do another one in the next example, and we'll use that little shortcut. So here comes my model. My model is going to be the amount at any time during as we go is going to be 6e to the natural log of 0.5 over 1,400 t. There's my model. Now let's go on and answer their questions. It says, then find the amount left after 4,200 years. Well, what I'll do then, the amount's going to be 6e, all of this in a parenthesis, natural log of 0.5 divided by 1,400 times 4,200. Let's go run that through real fast, and then we'll see what you get. And if you really think back through it, you'll also have it there. So let me jump over to the calculator. Let's go 6e to the natural log of 0.5. Let's close that off. Divided by 1400 times 4200. Now, like I said, this one came out nice because of certain numbers. So the amount we're going to have is 0.75 grams. And like I said, we'll put this in a sentence, which I have on the next page. Now let's answer the last part. How long will it take to decay to 1.5 grams? Well, my future amount's going to be 1.5. My formula is 6e to the natural log of 0.5 over 1400t. And then we'll solve this. Divide both sides by 6 and get 0.25 equal e to the natural log of 0.5 over 1400 times t. Boy, that's messy. Let's natural log both sides. So I've got the natural log of 0.25 equal the natural log of 0.5 over 1400 times t. And then to solve this thing for t, multiply by the reciprocal. So here's going to be my answer. The natural log of 0.25 times the reciprocal, 1400 over the natural log of 0.5. If you run that through your calculator, you're going to find that it's going to be 2,800 years. Like I said, this one was an easy one to toy with because of the numbers that we were using. 6, 3, 1.5. They were automatically halves of each other. On my next page here, though, I've got what it looks like in a sentence. The amount after 4,200 years is 0.75 grams. Based on our numbers, it wasn't approximately. And then that'll also take 2,800 years to decay to 1.5 grams. So there's 3 out of the 4. We're going to use our little shortcut on the next one and be done. So here goes. Assuming carbon-14 has a half-life of 5,730 years, give the approximate age of a skull found by an archaeologist if the skull has 63% of its original carbon-14 concentrate. Well, I know what the R value is, so I can skip some steps right now because it's half-life. I know the half-life of this is going to be the natural log of 0.5 over the half-life of 5,730. That saves me subbing in all those numbers already. So here's my model. My model is the amount that I want to talk about is, there's no starting amount, so I'm going to use 100%, so 1. E to the natural log of 0.5 over 5,730 t. Now here's how we handle this. To be truthful, guys, it does not matter what number that you put there. If you put 100 grams, I'm going to take 63% of it and get 63. If you want to put a 50 there, I'm going to take 63% of it and get, what would that be, 31.5? So we're going to pick the easiest number to work with. We're going to leave that as a 1, or 100%. So look down the road. To maintain 63%, if we started with 1, there's going to be 0.63 left. So I got 0.63 equal e to the natural log of 0.5 over 5,730 t. And we would like to solve this for t once again. So I'm going to take the natural log of both sides. So I got the natural log of 0.63 equal natural log of 0.5 over 5,730 t. Let's multiply both sides by the reciprocal. So I'm going to multiply over here by 5730 over the natural log of 0.5. Just run that straight through your calculator. So I'm going to have 5730 times the natural log of 0.63. Close that off. It looks like divided by the natural log of 0.5. So it looks like I'm going to get approximately 3,819 years. So in the form of a sentence, the skull is approximately 3,819 years old. So guys, there's our application problems with the trig. We shortened the assignment up just to kind of gain a day and give you the review sheet. So that should have only taken 20-21 minutes out of your day. Get a good jump on those review sheets. My answers will be posted by the time you get to this, so good luck on it.